Hello, everyone. Our goal today is to talk about GCDs and the extended Euclidean algorithm. It will turn out that the extended Euclidean algorithm is incredibly important computationally because it does something very complicated very quickly. And so, what is the thing that it does? Well, it does two things, but the first thing it does is to find the greatest common divisor of two numbers. So I want to remind you what the greatest common divisor of two numbers is. So if a and b are positive integers, then the greatest common divisor of a and b is the largest number d, such that d divides both a and b. In other words, it's the greatest of the common divisors of a and b. So it's exactly what it says on the tin. So just to give you an example, the greatest common divisor of 6 and 8, that will happen to be 2. Now, I'll note we can interpret this statement in terms of the prime factorizations of 6 and 8. So I could think, okay, 6 is 2 times 3, and 8 is 2 cubed. So what are the primes they have in common? Well, they both have 1, 2, and that's it. So the greatest common divisor is 2. As another example, I could take some larger numbers, like 120 and 241, and I could ask you what the greatest common divisor of these is. And now these numbers might be large enough that you look at this and maybe it's not immediately clear. But I'll give you a hint. 241 is prime. And so if you believe my hint, can you figure out what the greatest common divisor has to be? Well, if 241 is prime, that means the only divisors it has are 1 and itself. But because 241 is larger than 120, 241 is definitely not a divisor of 120. And so what that means is the greatest common divisor of 120 and 241 is actually 1. If you think about what it means for two numbers to have greatest common divisor 1, that's the smallest the greatest common divisor can ever be, because 1 is a common divisor of every pair of positive integers. But if the greatest common divisor is exactly 1, that's telling you there are no prime factors in common between the numbers. And that somewhat motivates the somewhat odd name that we give to this, which is that if the GCD of two numbers is 1, we call them relatively prime. Or sometimes you'll hear it called coprime. Now, note when we say relatively prime, we don't mean kind of prime. Indeed, it sort of sounds from the name, at least to me, like it should be one number that's relatively prime. But when we say relatively prime, we really specifically mean relative to each other. They have no common factors. Note, two numbers can definitely be relatively prime, even if neither of them are prime. So, for example, 24 and 35 are relatively prime to each other, even though neither of them is individually prime. So the question is, how are we going to calculate the greatest common divisor of numbers if the numbers are large? Remember, for cryptographic purposes, we're often going to be dealing with numbers that are thousands of digits long. So let's say you're given two cryptographic numbers, so two numbers that are each 1,000 plus digits long, and you're asked to find the greatest common divisor. Certainly the way we were doing this over here is completely infeasible. Namely, what did we do over here? We sort of said, okay, well, I'm going to just factor both numbers in my head, and then I'm going to look for the common factors and throw everything else out. Any proposal for how you're going to do something with 1,000-digit numbers that starts with factoring them is a losing proposition. Because, as we'll find out, factoring large numbers is basically impossible. Again, not that the factorizations don't exist, just at a certain point the numbers become so prohibitively large that none of the known algorithms are able to factor them. And so the reason the things we're going to do today are important and impressive is because I can actually compute this thing, the greatest common divisor of two numbers, that tell me something about their prime factorizations, but I can compute it without having to calculate their prime factorizations. So our entire algorithm is going to hinge upon one tiny observation that we made when we first started talking about divisibility. So let me remind you of what that observation was. If you start with two numbers that are divisible by something d, then no matter what combination you take of those two things, after multiplying them by some other numbers and adding them, the result is still divisible by d. So let me show you how this can potentially be useful. Namely, I want to hop back to the greatest common divisor of 120 and 241. Now, the way we did this before was to say, 241 is prime. But what we can actually do instead is to say, okay, let's suppose I have some number that actually does divide both 120 and 241. Well, what this proposition says is if I multiply these things and add or subtract them, it's still going to be divisible by that. So what I'm going to say is the greatest common divisor, it definitely divides b, which is just 1 times b, minus 2 times a. But that is just 1. And so what we're saying here, just to be clear, is anything that divides both 120 and 241 divides 1. And so once we know the GCD has to divide 1, well, then the GCD just is 1. This is the basic goal of the Euclidean algorithm. We're going to start with 2 big numbers, and then we're going to progressively produce smaller and smaller numbers that our greatest common divisor also has to divide, until hopefully those numbers are small enough that we can handle the question. So I'm going to show you the Euclidean algorithm by doing it for this particular pair of numbers. So here is 351 and 120. And so, again, I'm trying to find what is the largest integer that divides both 351 and 120. So, what am I going to do? Well, I want to find a smaller number that thing also divides. So again, I'm going to let D here represent the GCD of these two things. And so I want to find as small a number as possible that D also has to divide. So remember, any particular combination of these two numbers would also be divisible by D. So I could, for example, take 11 times 351 plus 17 times 120. If you do that, you get 5,901. And so whatever the GCD of A and B is, it also divides 5,901. So how is that useful? Well, it's not. Why is it not useful, whereas our example up here was? The reason why it's not useful is that 5,901 is actually larger than both of these numbers, and so I'm going the wrong way. My goal here is to produce a combination that is smaller than either of these numbers. And in fact, the way we're going to do this is going to be to use the division algorithm. Because if you remember, what's true about the division algorithm is that the thing you get as the remainder in the division algorithm is always smaller than the number you took as your denominator. So if I apply the division algorithm to dividing A by B, note I have to be taking the denominator to be the smaller number because I want the remainder to be even smaller. But if I do that, the division algorithm tells me 351 is equal to 2 times 120 plus, well, it works out to be 111. So what did we learn? Well, if I rewrite this equation just a little bit, I'll get 111 is 1 times 351 minus 2 times 120. And so this 111 here, it is a linear combination of 351 and 120, just like our proposition told us. And so I still don't know what the GCD of 351 and 120 is, but I know that whatever the GCD of 351 and 120 is, it also divides 111. So if you think about it, we started with these two facts. The GCD divides 351, and the GCD divides 120. And now we have a new fact. The GCD also divides 111. So what do we do from there? Well, we've made the problem a little bit better, because 111 is smaller than either of these two numbers. But actually, we can use the same logic that we just used, But instead of applying it to 351 and 120, we can now apply it to 120 and 111. So namely, I'm going to use the division algorithm, and I am going to divide 120 by 111 using the division algorithm, which will give me that 120 is 1 times 111 plus the remainder, and the remainder here is 9. So this 9 here is 120 minus 111. And so what that means is 9 is now also divisible by d, because remember, d divided both of these two pieces. This is a linear combination of those two things. And so we get to add to our fact bucket that the GCD, d divides 9. Well, you can probably guess what we're going to do now. Now, the GCD divides both 9 and 111, so I can produce an even smaller number that the GCD divides by applying the division algorithm to 111 and 9. So we apply the division algorithm again. And so we have to decide how many times does 9 go into 111. And in fact, 9 goes into 111 12 times. And indeed, 12 times 9 is 108. So the remainder here is 3. And so remember, again, 3 now is a linear combination of 111 and 9, and our GCD divides both of those. So our GCD now also divides 3. And so we can add that to our fact bucket. Now, we can keep going, and something interesting happens this next step. I apply the division algorithm again. I divide the smallest 2, so I divide 9 by 3, and I get 9 is equal to 3 times 3 plus 0. And in fact, the way you know you're done using the Euclidean algorithm is when you reach this point where the remainder is 0. So, in fact, actually, what turns out to be the case is every time when you get to 0, that means your previous remainder was the GCD. Well, why is this the GCD? By construction, the GCD definitely divides this number. It definitely divides 3 in this instance. And so if you think about it in this particular case, the GCD is either 1 or it's 3. And that's depending on whether 3 actually does divide both of 351 and 120. But if you look at our division algorithm step here, actually, I know that 3 divides 3, and I know that 3 divides 9 now. Why do I know that 3 divides 9? Because if I look at the last step, I got a remainder of 0, so that exactly told me that 3 divided 9. And so that means, putting these two pieces together, that 3 in fact divides 111. Why? That's our proposition again. 3 divides both of the pieces, so 3 divides their sum. But now, we know 3 divides 111, we know that 3 divides 9, 120 is the sum of those two, so 3 in fact divides 120. Well, now we know that 3 divides 111, and 3 divides 120, but 351 is 2 times 120 plus 111, so 3 in fact also divides 351. And so by rewinding like that back through the steps, what you see is that the number that ends up getting you a remainder of 0, that is the remainder before that, it always divides both of the numbers you started with. And so what we've really said here is this number that you get at the end of the algorithm, it both divides the GCD and is divisible by the GCD for different reasons. Remember, every step here preserved the fact that we were going to get something divisible by the GCD, but in fact, now by this argument I've just given you, the GCD actually divides this number, and so putting those two together, the GCD is actually equal to this number. Showing that something is equal to another number by showing that both divide the other is very similar to showing that two numbers are equal by showing they both are less than or equal to the other, or showing two sets are equal by showing they're both subsets of the other, whatever, same basic idea. Now note, at no point in this process did I need to know that 120 happens to factor as 2 cubed times 3 times 5, or that 351 happens to factor as 3 cubed times 13. I did not need to know either of these things, but I did correctly get that the greatest common divisor was 3, which if you now look at the factorizations, which I have just told you, 3 is the only prime that divides both numbers. 3, in fact, divides 120 once and 351 3 times, and so the GCD works out to be 3. But all of this algorithm worked without having to do any factoring. I got the right answer. I didn't have to worry about that at all. Before I write down a summary of what it is we just did, I want to ask one more question. And this is an important question to ask about any algorithm you intend to use for practical purposes. How do I know this algorithm is going to stop? Remember, we stop when we get to a remainder of 0. But how do I know that ever happens? And the key observation is that because we keep using the division algorithm like this, our remainder is always getting smaller. And so in this instance, our remainder went from 111 to 9 to 3 to 0. But regardless of how you apply this algorithm, the remainder will always shrink at every step. And since the remainder is a positive integer, or I suppose I should say a non-negative integer, because it can be 0, we will eventually get to 0 if we strictly decrease every time. And remember, what the division algorithm guarantees us is that we strictly decrease every time, because the remainder is always smaller than the thing you're dividing by. Okay, so let's summarize this algorithm. So if you think about this as a function in a programming language, how many inputs do we have? We have 2 inputs. Namely, I'm going to call them A and B, the 2 numbers whose GCD we want. Now, really, there's only one step to the Euclidean algorithm. It just happens to be a step we repeat over and over and over and over again, which is that we're going to divide the larger of A and B by the smaller of A and B. And you might have noticed, I didn't even care about the Q part of the division algorithm. I actually only care about the remainder. So I'm going to divide A by B, or B by A, whichever the bigger one is. I'm going to divide it by the smaller one. Come up with a remainder, call that remainder R. I might also compute a Q, but I don't need to keep the Q. So here at step 2, we should check whether the remainder is 0. So if the remainder is 0, then we're done. And upon stopping, we have to actually say what the answer is, and the answer is going to be the smaller of A and B. This is, again, what happened when we got to this last step here. When we boxed to the 0, that said, aha, we are done. I just need to go back and look, and so I go one step back and look at what the previous remainder was, which will be the smaller of A and B. Now, you might be inclined to say, wait a second, A and B are the inputs. But in fact, in this algorithm, I am not going to keep A and B representing the inputs. I am going to replace them because if this R is not 0, then I am going to replace the larger of A and B by R. And then I go back to step 1. So if you want to see what we just did in our previous example written up in this language, here's what we're saying. We input to the computer A equals 351, B equals 120. The computer divides 351 by 120, and when it does that, it calculates the remainder is 111. Now, it's maybe silly to point this out, but the reason we call the division algorithm is because it is literally an algorithm. So the computer is eminently capable of applying the division algorithm to calculate this. This number 111 here, it's not 0, so it is going to replace the 351, because the 351 was the bigger of these. And so now, we are going to feed into the same algorithm the numbers 111 and 120. And so what's really going on here, if you like the computer terminology, this is a recursive algorithm. I'm just outputting something that I'm going to input back into the same algorithm until I'm done. So we look at 120 divided by 111 now, and we calculate the remainder, and that remainder is 9. 9's not 0, so we put in the 9 for the 120, and then we do it again. The computer calculates now that the remainder is 3, still not 0, so the computer puts in the 3 for the 111. Now A is 3, B is 9, and so now again, the computer divides the larger by the smaller, but this time when it does it, it does get a remainder of 0. And so the computer notices that. The remainder is 0. That means I'm supposed to stop. And then I look back at the A and the B, and I say, aha, this is the smaller of the two, so that is the one we return. So we end up returning 3. So that is the Euclidean algorithm. And if you would all like coding, this is a very, very, very quick thing to code. So what I want to emphasize here, when I say this algorithm is quick, I mean it did take us like 10 minutes to do it for 2 3-digit numbers. But of course we're not computers. But, and here's the key thing, and I promise we'll talk about this a lot more, the difficulty of this algorithm, or the length of time it takes to run this algorithm, grows proportionally to the number of digits in the numbers involved. So if I take numbers that are, instead of being 3 digits, instead I take numbers that are 6 digits, the numbers involved are 1,000 times bigger, but the algorithm will only take twice as many steps. And so this is a very efficient algorithm. And so just to put that in context, let's imagine your goal is to find some pretty large primes. Now, your first step here might be generate some humongous number, and then check if it's prime. Now, if you're trying to be efficient, you might notice, for example, that the last digit of this random giant number had better not be even, or 5, because if it's one of those, the number's definitely not prime. There's no reason to even try. You might also think, okay, well, I can check whether it's divisible by 3 because I know this little trick, and 11 because I know this little trick. But in fact, what you can actually do is to calculate the GCD of this number, which remember is gigantic. I'm picturing that this number is like 1,000 digits or something like that, with, and let's say here, 1,000,000 factorial. Now, pause for a moment to appreciate how absurdly, ridiculously large 1,000,000 factorial is. And even though this number is preposterously large, it's about 5.5 million digits long, it is way, way, way larger even than our ridiculously large number that we want to be prime, this algorithm will run almost instantaneously on a modern computer with this gigantic 5.5 million digit number. And what are we hoping for? Well, we're definitely hoping that the GCD here is 1. Because remember, if this number is thousands of digits long, it had better not have any factors in common with 1,000,000 factorial. And so, in fact, this one GCD calculation, it actually, in one calculation, checks whether your number is divisible by any prime less than 1,000,000. Really, all I'm using there is that 1,000,000 factorial is definitely divisible by every prime less than 1,000,000. Because, well, when you write down 1,000,000 factorial, you've written down every prime less than 1,000,000 in the product. So, by performing this one gigantic GCD calculation, we can rule out all factors that are smaller than 1,000,000. And so if we find that the GCD is anything other than 1, we can just throw our number away and pick a different random number and start there. Now, if the GCD actually is 1, that doesn't tell us the number is prime, but it at least tells us our number doesn't have any small factors, and then we can look at a fancier primality test, like we'll talk about later, to try and actually vet the number and see if it really does turn out to be prime or not. So that just gives you some sense as to how powerful and fast this algorithm is and how it can be useful towards doing the kinds of calculations that we're going to need to do for cryptography. The astute among you will no doubt have noticed that I said at the beginning of the video that we were going to talk about the extended Euclidean algorithm, and I said those words a few times, and then I only talked about the Euclidean algorithm. which is suggestive that actually the algorithm we're going to talk about is a slightly different algorithm than the one I just described. And that's true, but the algorithm is not very different. Let me show you. And I'm going to show this to you by using the example, the GCD of 7,777 and 1,001. And really, all this version of the algorithm is going to amount to is going to be doing a little bit of bookkeeping while we do exactly the thing we did before. So I'm going to start by noting that if I look at ax plus by, which is this thing I've kept manipulating to keep track of the GCD, and I let x be 1 and y be 0, I just get a. So I'm going to write a into this table. And if I let x be 0 and y be 1, then of course I'm going to get b, which is going to be 1,001. And so the first step of the extended Euclidean algorithm is always going to be to make this table. Now, what did we do when we did the Euclidean algorithm? Well, we divided the bigger number by the smaller number. So I wrote 7,777 is, okay, and so that's going to be, I can do this, 7 times 1,001 plus, and then our remainder here is going to be 770. Now this remainder here, I am going to put into the next row of my table as ax plus by. But I'm also going to figure out what this number is in terms of x and y. And that's not so tricky because, well, 770 is, well, this literally tells me 7777 minus 7 times 1,001. So that is to say, this is 1 times a minus 7 times b. Again, each line of this table is just giving me an equation. In this case, the equation is 1 times 7,777 minus 7 times 1,001 is 770. The table is really just shorthand for this string of equations. So, what's our next step in the Euclidean algorithm? Well, now we're only looking at these two numbers, because we've thrown away the 7,777, or if you prefer, we've replaced it with the 770. So now I'm going to divide 1,001 by 770, again, using the division algorithm. So I'll get 1,001 is equal to 1 times 770, plus, and then what is my remainder here going to be? It'll be 231. So I will take this 231, that new remainder, I will put that as the next row in my table, and I will figure out how did I get that? Well, I got that 231 was equal to 1,001 minus 770. Or, if you prefer, it is 0 times a plus 1 times b minus 1 times a minus 7 times b. All I'm doing here is subtracting the equation that this line represents from the equation that this line represents. And so when I do that, I will get minus 1 and plus 8. Again, all this line says, just to emphasize, is that minus 7,777 plus 8 times 1,001 is equal to 231. Every row in this table is just a statement of an equation like that, and this one is, and you can check that this is true. If we keep going, we're supposed to divide now 770 by 231. That will in fact be 3 times 231 plus, and then my remainder here will be 77. And so now I have to fill in the remaining part here. What have I said? 770 minus 3 times 231 is 77. So this row minus 3 times this row is this row. So let's do that calculation. this row minus 3 times this row. That'll be 1 minus 3 times minus 1. So that'll be 4 minus 7 minus 3 times 8. That will be minus 31. Again, what does this now say? This says 4 times 7,777 minus 31 times 1,001 is equal to 77. You're very welcome to check that that is in fact really a true statement. And so what do? We now divide 231 by 77. Good job if you're one of the people who've already done this in your head and realize that this is the time when the remainder is 0. And so we can copy our remainder of 0 there into the table. And so what does that tell us? That tells us the GCD is 77. But, and here's the thing that makes this the extended Euclidean algorithm, it also told us these numbers x and y. So we learned not just that the GCD is 77, but also that 77 is this combination. It is 4 times this minus 31 times this. Now, at first blush, maybe you're not impressed by the fact that we found these two numbers that allowed us to multiply by the things we started with to get the GCD. And that's fine. If you don't care about these numbers, you can just use the regular Euclidean algorithm and you'll get the GCD and it'll be fine. However, it will turn out, for a variety of reasons, that we often might want these two numbers. And so, for example, next week, when we're going to calculate modular inverses, it will turn out that we want to solve exactly this equation, and then by marvelous coincidence, it will happen we already have an algorithm to solve it. And so the calculation of these coefficients here in front of the two things we took the GCD of is something your computer is doing in the background all the time. And so next week, we'll figure out why. On the other hand, though, I want to point out that what we've actually done here is actually noted an interesting theoretical result, which is that, in fact, it's always possible to express the GCD as a combination of this sort, as I keep calling it, a linear combination of the two numbers it's the GCD of. Now, you might think, wait, isn't that exactly what you started with, this observation that the GCD has to divide this linear combination? And yes, I did start with the observation that the GCD has to divide this linear combination. But in fact, what we've shown is much better. We've shown that it's always possible for the GCD to equal this linear combination, as long as you choose the right x and y. So I'm going to record that fact as a theorem, because this theorem is quite often useful in proofs, in addition to being useful in computation. Now, I grew up calling this Bezout's theorem. Apparently, only people in France and the people who taught me call this Bezout's theorem, but I'm going to call it Bezout's theorem anyway. If a and b are any two positive integers whatsoever, then always there exists x and y in the integers such that their combination ax plus by is exactly that GCD. We will quite often apply this in the instance where a and b are relatively prime. That is, if a and b are relatively prime, this says that it's always possible to get a linear combination of a and b that's equal to 1. Because remember, relatively prime just means GCD of 1. But you'll have opportunity on the homework to apply this in instances when the GCD is not actually 1. And the beautiful thing is, if you believed me when I claimed to have proven that the Euclidean algorithm worked, then you have to believe me that the extended Euclidean algorithm worked, because all I did in the extended Euclidean algorithm was keep track of what each step was saying in a table. And so that also means that you believe we've proven Bezout's theorem. Because, of course, if we have an algorithm that's guaranteed to produce these x and y, then, of course, these x and y have to exist. Now, you're welcome to feel I waved my hands a bit, and maybe this wasn't really a proof, and maybe that's kind of in the spirit of this whole class anyway, but proofs of these claims are readily available online, so if you want to go back and go over the details of why exactly the Euclidean algorithm works, why exactly the extended Euclidean algorithm always guarantees you that you'll get the correct combination, and so hence why Bezout's theorem is true, I'd encourage you to do so. For in-class quizzes that we'll have, what I will want you to be able to do is to implement the extended Euclidean algorithm. And so if I give you A and B, I'll want you to be able to give me matching X and Ys that give me this GCD. As long as you can master that, you'll have understood the skill you need to out of this video for purposes of in-class work. Last up today, I want to make a remark about what happens when you allow in 0 into your definition of divisors, and what happens when you allow negative numbers in, and how those interact with GCDs. So the first observation is that every number divides 0. And that's for the simple reason that if you want to show that A divides 0, all you have to do is to show that 0 is a multiple of A, and in fact, 0 is, well, it's 0 times A. And so, in some weird sense that I would not want you to think about too hard, 0 is sort of the product of all the primes, rather than maybe the opposite, because all the primes divide 0, and so rather than 0 sort of having no primes in it, that's kind of what 1 is. 0 actually sort of has everything in it. And so as a result, if you do take the GCD of some positive number and 0, well, this is asking you what's the largest number that divides both A and 0. Well, literally every number divides 0, so this GCD just ends up working out to be A. If you like this kind of gross technical thing, it actually makes our description of the algorithms today a little bit nicer, because you'll see at the end when I say, okay, just return the previous step, what you're actually returning is really still the GCD of these two numbers. It's still the GCD of 0 and 77, or whatever it happens to be, because the GCD of anything in 0 is just the anything. But I should warn you, this still leaves one really awkward case, which is the GCD of 0 and 0, which is just always undefined. There is no largest number that divides 0 and 0, because, well, every number divides 0 and 0. This is all a technicality. I don't intend this to come up. I'm just noting this for completeness. Now, sometimes you might want to think about GCDs with numbers where one of them is negative. So you might want to think about something like, what is the GCD of minus 14 and 21? And if you do that, basically the thing is you just forget the negative. Because if you think about what primes are going to divide minus 14, well, if you think about what that has to mean, it's going to be 2 and 7. And so that's the same primes that divide 14, so you might as well just use 14 instead of minus 14. So whenever someone takes a GCD with a negative number, you're always going to get something positive back. And the positive thing you're going to get back is the same thing as if the minus wasn't there at all. Okay, we'll wrap up talking about GCDs and divisibility there for now. Next week, our plan is to start talking about modular arithmetic and remainders. And it will happen that GCDs and Bezout's theorem and the extended Euclidean algorithm will factor in an enormous way into that discussion. But that's all for now. Have a great weekend, and I'll see you next time.